So good afternoon, everyone. My name is Scott, and as Manoj introduced, I'm from the Core OS team at Microsoft. And today, Ray and me are going to talk about multi-tier memory in Windows and also Azure. So in the first half of today's talk, I'm going to give a directional sharing on multi-tier memory support that we're planning on Windows and how we're intending to expose multi-tier memory to applications. In the second half of the talk, Ray is going to be talking about potential usages of multi-tier memory in Azure. So as multiple folks have already explained, if we look out into the future, we are going to see memory devices that's going to have a variety of different performance characteristics. It's coming soon. We have high bandwidth memory, which is expected very soon on servers. We have CXL memory devices that are going to be a little bit further along, but again, it'll start appearing. So with all these memory devices, they have performance characteristics that are very different sometimes than what we have today with DDR memory. So by performance characteristics, the primary things that I'm thinking about are things like latency and bandwidth. So as we look at this coming trend of memory devices with varying performance characteristics, the way we're viewing this is that realistically, we have sort of two categories of memory. We have the general purpose memory that we have today, and then we have a new category of memory that we're using the term dedicated memory for. So for general purpose memory, it's the memory that we have available on today's system. This is memory that's managed by the operating system's memory manager. The memory manager will use features such as paging or compression to try to make that pool of memory be more than what's actually physically there for applications to use. General purpose memories are allocatable by anyone. It contributes to system commit. So if you were to ask me, Scott, what is the performance characteristics going to be for general purpose memory? I would say that right now, I don't really have an answer for it. If we were to look at today's software, a general guidance for today's software is if your performance latency is equal to or up to a NUMA node difference than DDR memory, then it can be considered general purpose memory. The new category of memory that we're going to see in the future is something that we call dedicated memory. A dedicated memory will be available through to application software through dedicated APIs that are different from today's APIs. It will not contribute to system commit. And for the performance characteristics of dedicated memory, it's going to be different than general purpose memory. The performance could be either higher or lower, or even it could be equal to the performance that's available in the general purpose memory category. On this system, we expect that there can be many different dedicated memory types that could potentially reside on a single system. From the operating system's perspective, obviously the operating system has to have a way of discovering on the system, are there any dedicated memory available? So from a Windows perspective, we are planning to leverage mechanisms that are already defined today in ACPI and UEFI to discover dedicated memory that's on this system. Our expectation is that dedicated memory will be described in memory-only NUMA nodes within the ACPI SRAT table. In terms of performance characteristic reporting, we are planning to leverage the ACPI's HMAT table and also the CDAT table that's been defined for CXL memory device to get understanding of, for a particular dedicated memory type, what its performance characteristics are. In terms of platform firmware, We were expecting platform firmware to report the areas of the system address map that has been assigned to dedicated memory devices. We're expecting platform firmware to mark those as either reserved or with a special purpose memory attribute. From an application software perspective, we will be providing new APIs that allows applications to be able to discover on the system what are the dedicated memory types that are available. Like I mentioned, and multiple other folks have mentioned earlier, we're going to see systems in the future that's going to have memory of varying characteristics that's going to reside on the system. So we want to build an infrastructure that doesn't assume anything about the number of dedicated memory types that can be present in the system. So in our view, each dedicated memory type will have a unique combination of attributes. So in our initial plan implementation, we are planning to expose 4 attributes: read latency and bandwidth, and then write latency and bandwidth. As we look into the future, we definitely expect the number of attributes to grow. So we will create APIs with the flexibility to be able to support additional attributes as we discover the need for it. In terms of the performance characteristics that the operating system will report to software, our plan is to use the speed of the media outside of any intermediate caches that may be present in the workflow, and also from the closest CPU node. So we want to take a very conservative approach in terms of reporting of the performance characteristics of the application, so that we're not reporting something that may only occur part of the time, but not all of the time. What we want to do to begin with is report characteristics that will happen all of the time, and then if we discover in the future there are benefits of reporting, hey, besides this worst case, there are potential cases where you could get better cases, where because you happen to hit some intermediate caches, then we may add that support in the future. But to begin with, we want applications to build assumptions based upon what they can see all the time. In terms of the new APIs that we are planning to expose, we will have an API that enumerates all of the dedicated memory types that are available on the system. We will also provide APIs for applications to allocate or free memory from a specific dedicated memory type. As alluded to earlier, that the presence of a dedicated memory, it isn't only reserved for application uses. Obviously, from the OS perspective, there are features within the OS where we can take advantage of dedicated memory if, say, there are no applications using it. So some potential usages of dedicated memory within the OS's memory manager are to use it as, say, a faster page file, or to use a dedicated memory as a secondary store for standby pages or for compressed memory pages. Obviously, the goal of the session isn't to enumerate all the possibilities, but these are just some of the examples of how within the OS we could take advantage of dedicated memory that can be available on the system in the future. So next, I am going to turn the talk over to Ray, who will talk about some potential usages of multi-tier memory within Azure.
Hey, anybody hear me? So yeah, this is Ray from the Azure Core Compute, HPC team actually. So as Scott said, right, so right now we are going to talk about 2 potential scenarios, using the multi-tier memory inside Azure. So we are using the existing, software operating system and also the architecture we are not actually yet, gone to the picture actually mentioned by Scott yet. So the first one we are talking about is actually the Zero Infinity, software product. So thanks to the Microsoft Deep Speed team, we actually offer the PowerPoint slide to us. So basically, it's a software stack that manages multi-classes of different media, and the goal is try to scale up the model training in deep learning without the code refactoring. So the second scenario we are talking about is actually using the file memory as an OS page file. And this is a Microsoft internal hackathon study. So we try to study the performance impact for the machine learning workload owned by our Microsoft research team, and trying to see if we use the file memory as an OS page file, how does that one impact the application performance? And also, as still, we also don't need the application code to be refactored in order to run on the operating system paging, because that one is already built inside the operating system itself. So the first slide, I'm going to talk about the Zero Infinity, why we are here. So as lots of the folks I talked about in the previous slide before, so thanks to the Golami actually from the UC Berkeley, they actually are collecting this kind of statistics. So as you can see, the red line is the demand, from the AI training model. They actually increased, from time to time all the way, So, and the green line is actually the current GPU memory size that is relied by the AI model. So as you can see, the line is actually pretty flat comparing to the demand. So in this case, the AI is actually hitting the so-called memory wall. So that's why we are thinking about the deep splitting, They are thinking about there's an opportunity to utilize another separate tier of the media, which can be larger, cheaper, actually to get into this picture. So what is a Zero Infinity in the high level? So basically, it's given a certain AI training model. It tries to break down each them into individual small jobs, and try to schedule onto the individual the GPU, CPU, and NVMe's system component, and move the data across different classes of media in order to finish the job. So this is essentially very similar to the traditional map and reduce methodology we are familiar with. So also the key point right here, comparing to the old way we are doing for example, like a 3D parallelism methodology, trying to scale up the AI model. This particular methodology, there are two key points. First one doesn't require the code refactoring. The second thing is that also try to leverage the larger size NVMe storage from that in the existing architecture. So as a result, sharing. So this one is already published inside the Microsoft blog, and also the source code is also available via the GitHub. So the key message I want to deliver from this one is comparing to the traditional 3D parallelism. So as the number of parameters inside the AI model keep increasing, this particular Zero Infinity is able to catch up based on the scalability. And also on the chart, there's no pointer. On the top, right point figure, it actually shows up the per GPU throughput. Once we increase the number of model parameters from 1 to 20 trillion, so the old model doesn't actually catch up, while the per GPU for the Zero Infinity can still catch up. So as a result, as you can see the bottom right figure, the overall throughput of the whole system training can actually increase linearly. So that's one of the key points. So for the Zero Infinity. So as a result, we are seeing the potential to use the file memory. When I say file memory, it's actually a cheaper, slower comparing to demand. Can be any media, any media on the CSL bus. So the potential to use the file memory as additional class of media inside of the Zero Infinity picture actually. So that's the use case of the first one. So the second one is actually, as I say, it's actually done internally inside Microsoft. We try to study some of the operating system paging performance on file memory. So the goal is try to replace the DRAM with file memory, cheaper, slower, with better costs. The the workload we are trying to use is actually from Microsoft research team. Is a sample workload is actually the pure memory application running machine learning, which is rely on the memory caching. So we are using the Windows OS 2019, no problem. So workload itself, right, the profile is actually a 32-thread workload, and the memory it committed, it takes 150 gigabytes of the memory. So the system, we are comparing two of the settings. The first one is a virtual CPU VM with 256 gigabytes of DRAM, which means that all the working set actually can be located inside the DRAM. The second one is actually we take down half the memory. We replace it with the file memory, configures the OS page file, and which means that 17% roughly about the working set is actually on this particular file memory media. And as you can see the right-hand side, the machine learning workload we pick up, right, they care about the latency percentile from 50 all the way to 39. So comparing to this particular two setting, we are not seeing any difference, and also latency drop, latency increase, between these two config. So the one thing I want to highlight is that the operating system doing the paging itself, we are measured in microsecond level. So which means that the media we are trying to fit into this particular picture not necessarily have to be the 1 NUMA hub away media, but can be something cheaper, but also slower and more cost effective. Yeah. So the end of the summary is the system with the multi-tier memory are coming, right? And the work is definitely needed to take advantage of this new hardware. So Azure is interested in using the multi-tier memory, right, to optimizing the existing service and also the work. So thank you all. That's all I have.